Hey everyone, it's Mrs. Brimlow. Today we're going to review our exponent rules and scientific notation. So please make sure you have your packet out so you can copy down the examples as we go. Before we can get into scientific notation, we have to start with our exponent rules. So these exponent rules can make it simpler for us to simplify expressions with exponents. So we're going to run through these rules quickly, and all of these examples are similar to what you can expect to see on RICAS. So starting with our product rule. Our product rule says that if we are multiplying with like bases, so that means they're the same, you can add the exponents together. So if I have b squared times b to the 7th, I would keep the base b, and 2 plus 7 is 9. For the quotient rule, if I am dividing with like bases, I would keep the base and then subtract the exponents. So x to the 8th over x to the 3rd, I would keep the x, and 8 minus 3 is 5. Power of a power rule claims that if I have a base and a power raised to another power, I would multiply those exponents or powers together. So in this case, I'd keep my base x, and 3 times 4 is 12. Power of a product rule states that when you have a product inside of parentheses raised to a power, you apply that outside power to each of the bases inside. So xy squared to the 5th. So on this x, I really have a power of 1. So 1 times 5 is 5, so x to the 5th. And then 2 times 5 is 10, so it would be y10. Same thing if I'm working with quotients. So x to the 3rd to the 2nd would be x to the 6th. And then this would be y to the 4th, because 2 times 2 is 4. My 0 rule tells me that anything to the power of 0 equals 1, so x to the power of 0 would just be 1. Now you have to be careful with how things are written. For example, 9x to the power of 0. What this is really saying is 9 times x to the power of 0. That exponent of 0 is only attached to the base of x. 9 is a coefficient. So this is really saying 9 times 1, because x to the power of 0 is 1. So this would be 9. If I had both 9x and x inside parentheses raised to the power of 0, just like we saw in this example, I'd be applying the 0 to the 9 and to the x, so that would give me an answer of 1. So parentheses are really important when we are working with these problems, so pay attention when you are simplifying these examples. So when we're talking about negative exponents, in order to make an exponent positive, we take the reciprocal. So for example, if I have x to the negative 7, to make this positive, technically I would see this as over 1, so I would take the reciprocal or flip it. So now it would look like 1 over x to the 7th. When it's in the denominator, we would still do the same thing. We're going to flip it, so it would look like x to the 5th, and you might say over 1, which is the same as saying x to the 5th. So we have a couple examples we're going to try putting multiple rules together. So starting with this example here, we'd start with parentheses. That's what order of operations would tell us to do. So I'm going to keep the 4. So this is power to a power. So I'm going to have 2, and then 2 times 3 is 6. So if I'm simplifying this, I'm going to keep the 4 still, and I'm going to simplify 2 to the 6. That means 2 times 2 times 2. You're going to do that 6 times. When I do that, I'm going to get 64. And then I'm going to multiply 4 times 64, which gives me 256. You most likely will not have calculators on a problem like this. A lot of these, I'd say 95%, will not give you calculators, so you'll need to do the work on a scratch paper if you don't know this. But my final answer would be 256 when simplified. Okay? All right, so looking at this next problem, I have to deal with the numerator first. I need to simplify the top so I have just one term at the top, and then we can continue on. So this is the product rule. So I keep my base, and I'm going to add my exponents. Negative 4 plus 5 is 1, and then I'm just going to carry over this 2 to the negative 2. So you could approach this next part in several ways. It is written as a fraction, so I could use the quotient rule. I also have a negative exponent, so I could make this positive first and then keep going. I would use, if I was doing this, the quotient rule. So the quotient rule tells me that I'm going to keep my base, so 2, and then I'm going to subtract. So I have 1 minus negative 2. So I'm subtracting a negative, okay? You always have subtraction, and then you just go with whatever the bottom number is. So according to rules of integers, I would end up adding the opposite or adding them together. So my final answer would be 2 to the third, which is 8. All right. So now this can help us work with scientific notation. So scientific notation is a way to take numbers that are either really large or really small, meaning they're going to have a lot of digits to them. They're going to be long numbers, and you can write them in a shorthand, smaller way. So in scientific notation, you have a coefficient, and then you have a base 10. As we talked about before, 10, 100, 1,000, those base 10 numbers allow us to move decimals and write numbers in equivalent formats. So, and then the exponent is going to tell us how we're moving our decimal point. So if I'm starting by converting from scientific notation to standard form, so we would call this scientific notation. This is standard form, how we typically write numbers. Okay? The exponent is going to tell me exactly what to do. If it is a positive exponent, you're moving your decimal to the right. It's going to be a whole number greater than 1. And the number itself tells you how many times to move the decimal. So I'm just going to rewrite the coefficient down here. So I need to move this decimal 6 times to the right. 1, 2, 3, 4, 5, 6. Now in those empty loops would be zeros. So if I rewrite this number, it's going to be 2,704,000. So in this case, if it's negative, I'm moving the decimal to the left. So it's going to be a number less than 1. It's going to be a decimal. So I'm going to move it 1, 2, 3 times. And just like before, those empty loops would have zeros. So this would be my final answer. Now, if you're trying to write numbers in scientific notation, in standard form to scientific notation, you need to move the decimal so the number is the coefficient is between 1 and 10. So I'd want to move this decimal right here between the 9 and the 5. So it would look like 9.52. When you write your coefficient, you need to include every non-zero number, okay? Times 10. So we'd have to move this decimal 1, 2, 3, 4 times. Because the original number is less than 1, it would be negative. Or to get back to the original, it would move to the left. So right now in this last one, the decimal would be here at the end. So when I move this to make it so that the number is between 1 and 10, the coefficient, I would move it between the 4 and the 0. Now when I write the coefficient, it's going to look like 4.09267. So we wouldn't stop at the 0, we'd include the 0 because we'd have to keep going to include all non-zero numbers. Times 10. Now to move it back to the original spot, I have to go by 8 spaces or 8 digits. And it would be a positive 8 because I'd want to move it to the right and make it a whole number larger than 1. Now, I do want to do one more example. You could do this off to the side on your paper if you want to. I'm going to do it on a sticky note. So, not only did we learn about working with converting numbers between scientific notation and standard form, we also learned operations. So, let's say I have 4.2 times 10 to the 7th, and then multiply that by 2 times 10 to the 4th. Just making this up. This is just a random problem. So when you're multiplying with numbers in scientific notation, because everything's being multiplied, we can use the commutative property to move these around. So I would rewrite this to be 4.2 times 2. Those are my coefficients. And then 10 to the 7th times 10 to the 4th. So I'd multiply the coefficients, which would give me 8.4. And then we know it's going to be times 10 because it has to have a base 10. And by rules of exponents, multiplying with like bases, you just add them together, so you get 11. You need to check to make sure that your final answer is in true scientific notation. That means that this number is between 1 and 10. If it is, your answer is done. If it's not, then you have to move the decimal, which also affects your exponent. Okay. Now division is going to work similarly, so I'll actually just use the same number. So if I have 4.2 times 10 to the 7th over 2 times 10 to the 4th, so we'd apply the operation to our coefficient. So 4.2 divided by 2 is 2.1 times 10. And then with division of like base and a quotient of like bases, we keep the base and subtract the exponents. So 7 minus 4 is 3. Same thing, I check to make sure this is in true scientific notation. If not, I'm going to move the decimal and change the exponent as needed so that they match.